Hello and welcome to Edu Aspirants, our YouTube channel for competitive exams. This is the second of the two videos on heat and thermodynamics. Let us begin. Work. Work is the transfer of mechanical energy between two systems. Now consider a gas container fitted with a movable piston. At equilibrium, the volume of the gas is V and it exerts a uniform pressure P on the walls of the piston. The piston has a cross-sectional area A. The force exerted by the gas on the piston F is given as P into A. Now the work done by the gas is, we can calculate small work done dW as F into dy, where dy is the displacement of the piston. F is equals to P into A into dy. A into dy, area into displacement is volume. So we can write dW is equals to P dV and W is equals to integration of P dV, and the limits are from V1 to V2. Work done on the system is negative and work done by the system is positive. We can take an example of a compressor. In compressor, we have to do work, so the work done is negative, and in the case of turbine, the work done is positive. First law of thermodynamics. It states that the heat energy supplied to the system increases the internal energy of the gas, and rest of the heat energy is converted into the work done by the system on the surroundings. Delta Q is equals to du plus delta W, where delta Q is the given heat, du is the change in internal energy, and delta W is the work done. We are using the symbol delta Q over here is because work done and heat transfer both are path functions, and du is internal energy, which is the point function. Thermodynamic processes. First one is quasi-static process. A very slow process and the system is always maintained in thermal equilibrium. Second one is reversible process. A process that can be made to reverse its direction of flow by changing the physical conditions, and it is considered that there is no dissipation of energy. Third, cyclic process. Any process where a system returns to its initial state, the change in the internal energy of the system is du is equals to 0. Fourth, isochoric process. A process in which the volume is throughout constant. Equation of state becomes, and the work done is isochoric processes, W is equals to P dV, where change in volume is 0, so P into 0 is 0. So work done is 0 in isochoric process. In isobaric process, a process in which the pressure is throughout constant. Equation of state becomes, and the work done is V1 upon T1 is equals to V2 upon T2. Now the formula of work done is P dV, so we can write P into V2 minus V1. Isothermal process. A process in which the temperature is constant throughout. Equation of state becomes, and the work done in isothermal processes, P1 upon V1 is equals to P2 upon V2, and W is equals to nRT natural log V2 by V1, or nRT natural log P2 by P1. We can convert natural log into log with base 10. We have to multiply this digit with 2.303. Next one is adiabatic process. A process where there is no heat exchange takes place between the system and the surrounding. W will be equal to P1V1 minus P2V2 upon gamma minus 1, or is equals to nR T2 minus T1 upon gamma minus 1, where gamma is adiabatic coefficient. Specific heat at constant pressure, denoted by Cp, it is the amount of heat energy required to raise the temperature of 1 mole of a gas by 1 degree of Celsius at constant pressure. Cp is denoted as delta Qp upon n delta T. Next is specific heat at constant volume. It is denoted by Cv. It is the amount of heat energy required to raise the temperature of 1 mole of a gas by 1 degree of Celsius at constant volume. It is denoted by Cv is equals to delta Qv upon n delta T. We can also write delta Qv as delta U, which is change in internal energy upon n delta T. Mayer's equation. In this equation, as we can see that Cp minus Cv is equals to R, where R is universal gas constant and its value is 8.314 kilojoule per mole Kelvin. Cp here is specific heat at constant pressure, and Cv is equals to specific heat at constant volume. Gamma, as we have discussed in adiabatic process, gamma is adiabatic coefficient and it is equals to the ratio of Cp upon Cv. PV diagram of some thermodynamic process. First one is isoporic process. As we can see in this PV diagram, we have to draw a line which is parallel to the y-axis. In this, volume is constant. Next is isobaric. In isobaric process, we can see that the line is parallel to the x-axis and pressure is constant throughout. Next is isothermal process. In the isothermal process, we have to draw a line which is a rectangular hyperbola. In adiabatic process, we have to draw a line which is a rectangular hyperbola, but the slope of adiabatic curve is greater than that of isothermal curve. Heat engine. A heat engine is a device that converts heat energy into mechanical energy through a cyclic process. As we can see, there is the hot reservoir, we can call it as source, having temperature T1. We have to draw the heat Q1 from here. Some amount of heat is converted into work done and some is given out to the sink, that is cold reservoir at temperature T2. Efficiency of heat engine. Eta is given as 1 minus T2 by T1, where T1 is the temperature of source and T2 is the temperature of sink. We have to keep in mind that both the temperatures are in Kelvin. Refrigerator. Now, hot reservoir, that is source, temperature T1, and cold reservoir, that is sink, temperature T2. Now we are taking out the heat from T2, that is Q2, to the refrigerator. So we have to do some external work through it, and the Q1 heat is supplied to the source. Coefficient of performance of refrigerator. It is denoted by beta, and beta will be equal to T2 upon T1 minus T2, where T1 is temperature of source and T2 is temperature of sink, and both are in Kelvin. This brings us to the end of the topic. Thank you for viewing. The next topic will be uploaded soon. Till then, keep revising and practice papers. To test your comprehension will also be uploaded soon. Subscribe and press the bell icon for notification of uploads. Share and like our video.